Hello, good morning. Am I audible?
Yes, sir.
Okay, last time we started with inverters, which will be required for solar power generation or solar power we want to feed to the grid. We'll just take a review quickly what we have done last time. So there are two systems. Okay, we have shown it here, a generalized single line block diagram of a transformer-less system. We don't have a transformer between the grid and the PV panel system. So here you have seen it. This will be our solar power generation. We are having a PV array, then a filter capacitance, then DC to DC converter, then voltage source converter, and this is feeding power to the grid. We require a line filter. So here we don't have a transformer in between the grid and the solar power generation. We have seen the importance of DC to DC converter. So in this case, the purpose of DC to DC converter is one thing is you match the voltage level required for the input of the inverter. Depending upon grid voltage, we should have a specific value of DC voltage. If we don't use the transformer, so we require a specific value of DC voltage. That is to be maintained with the help of this DC to DC, normally a boost converter. And another important job of this DC to DC converter is operate this PV array or operate the solar panel at the maximum power point tracking. Okay, so that is the purpose of this. And you have seen that this is a voltage source converter, or you can call it as a PWM rectifier and the PWM inverter. And power flow is bidirectional, we can say it here, but in this case we require only power flow is unidirectional. So here our active power flow is this direction. Okay, active power is flowing from, this is you can call as a P, that is active power flow is flowing from uh, PV panel to the grid. But our reactive power flow, it can be a both directions. Depending upon the grid requirement, it is possible, this converter or voltage source converter, it is possible that our Q, either we can absorb or we can deliver the Q. So we can provide a lagging reactive power or the leading reactive power. So that is the importance we are having here. So active power is flowing from this solar system, solar PV system to the grid. This is a grid. Whereas the reactive power exchange, both can be possible. A reactive power flow will be from grid to the inverter or from the inverter to the grid also possible. So some applications definitely we require isolation between the this PV system and the grid. And if you put the isolation, we are involving cost of the transformer and losses in the transformer. So now people are trying to have a system which will be having a transformer less. And if you are having we can put a transformer if it is required, and then, but nowadays we are not preferring transformer. A transformer is a bulky one thing, and losses associated with will be also there. Transformer is having efficiency maybe 95%, but overall efficiency of the system may reduce to 1 to 2%. So that is not required. So our interest is we should have a grid connected PV system without a transformer. That is what our intention. And now we have just classified the inverters. Our more trace is now on the inverters, and these inverters, depending upon the capacity, we are classified as module integrated inverter, string inverters, which will having a 400 watts to 2 kilowatt. So here how the circuit will look like. So this is the first A, that will be module integrated. We are having a module in that we are having DC DC converter, then DC to AC inverter, and this connected to the grid. This is a module integrated inverter, you can call it. Another is a string. We should have a solar panels connected in series for to getting the required DC voltage, and then we can have. So this will be called as a string inverter. Then here we are in mini central inverter. If you see the third diagram, so we are having the three single phase inverters. If you see it here, One inverter is a single. We are having a string inverters. Three string inverters we are connected to form a three-phase system, a three-phase grid, and that is called as a mini central inverter. So this will be a one string for phase A, another string for phase B, and third will be for phase C. That will be a mini central inverters. Then multi-string inverters, we are having a more number of strings here connected, particularly in series, number of panels we connected in series, and each panel we are having a DC to DC converter, and then this we connected to us in particularly this we can call as a multi-string inverter, this configuration. Whereas another is we are having a central computer for big capacity. We can connect the panels in parallel and series to get the, and we feed the power. If you go back capacities, a string inverter is having capacity a small 400 watt to 2 kilowatt. This may be particularly suitable for our small rooftop uh, solar power plants. Multi-string, we have seen it here, a multi-string. So this will be a D, that will be a multi-string, and that may be a 1.5 to 6 kilowatt. Mini central inverters, we can go up to 100 kilowatt, 6 kilowatt, and the central inverters, we are having a 100 kilowatt to 1 megawatt. So this is the configuration we are having. And now our interest is more on whatever this particular lecture, solar PV inverters we are having. We are more concentrating on the single phase inverters. Our basic intention is for the single phase. Last time we discussed, we require the inverters for a speed control of induction motor. Also, we require the inverters for feeding power to the grid in case of wind or solar. But the PV inverters are more complex than the motor drive inverters, and we listed the reasons last time. Okay, so we listed the reason. First reason is we need the boosting of the DC voltage. Whatever the solar voltage, we may have a solar panel voltage may be a less, and we want to boost for the required to the level of the grid voltage, so that boosting of the DC voltage. Then we require a filter at the grid site. That is second requirement. When there is a problem in the grid or fault in the grid, we have to grid disconnection relay required. We require DC switch. These are the hardware requirements, as well as we should operate the inverter at maximum power point. We can isolate the inverter during fault in the grid. We have to auto closing, that is grid synchronization is required. We have to connect the inverter to the grid, and all this we want to be a data logging is required, active reactive power, a number of units consumed, that data we should be available online, data logger is required. So these are the functions required for a PV inverters as compared to a drive inverter, motor drive inverter. So MPPT, anti-aliasing, grid synchronization, data logger, these operations are not required in case of a motor drive inverters. Whereas these operations are required in case of a solar PV inverter, and definitely PV inverters is more complex as compared to a motor drive inverters. And now we are already discussed why we avoid the transformer in between the grid and the solar PV system, and we are removing the transformer. The sole purpose is our efficiency improvement maybe 1 to 2%. So their overall efficiency improvement is almost 2%. Uh, and now, but we have seen that solar panel, what are the components? It will be a glass semiconductor rounded metallic frame, and this will be a forming a capacitance between the panel and ground. So that is one issue that is very important in case of solar PV panels. That will be a capacitance between the panel to the ground. Capacitance between the panel to the ground, that is very important, and the value will be increases with number of panels are increased. So 10 nanofarad per kilowatt, that will be approximate value of this uh, capacitance between the panel and ground. And because of this capacitance, we are having a leakage current, particularly in the system. The current will be flowing between the panel to the ground, that may be, and that is the reason. So we want to minimize this leakage current so that safety of the personnel working on that will be ensured. So more interest, we have seen that we can go for a transformerless uh, inverter system. We don't require the isolation transformer, we avoid it. And now some of the companies, they are manufacturing this type of inverters where we don't require the isolation. And these companies are, one is SMA, second is Sunways, third is Conergy, then Ingeteam, Danfoss Solar, and Ripu. These are the companies. They are manufacturing the solar PV inverters, and the efficiency is approximately in the range of 97 to 98%. All these manufacturers claim this is a inverter efficiency, not the solar efficiency overall system. Only inverter, they are claiming the efficiency will be around 97 to 98%. And now our interest is, we want to see the feasibility why our full bridge inverter is not suitable for solar inverter. Okay, we have seen that a full bridge inverter is suitable for motor drive applications, but our full bridge inverter, which is consisting of four switches, is not suitable for grid connected solar system. Is it clear? Any questions? Hello, am I audible?
Yes, sir, you're audible.
So what is our intention now? We are having a single phase full bridge inverter. If you see, is it visible? Screen is visible.
Yes, sir.
So this is our single phase bridge inverter. And now we want to prove, okay, that this inverter is not suitable for PV inverter. This is not a suitable configuration for the solar PV inverter, which is feeding power to the grid. Now we go how it is not suitable, we can discuss. Here let us consider this will be our PV panel. Okay, and the PV voltage of PV panel is represented as a VPV. That is the a panel voltage. It may be a, okay, number of panels connected in series parallel configuration, and this will be a PV. And here if you see, we require a capacitance here. Okay, if it is a feeding power at the DC side, we require the capacitance. Power balance is the purpose, we require the capacitance. Here whatever the solar panel will generate, what type of power it will generate at a particular, with respect to time, how is the power generated by the solar panel will generate a constant power. Okay, this will be a power generated, constant power is generated by the solar panel, a particular radiations. We say that our power output is a constant. But in case of this grid, how is the power flowing? How is the power? If both were having in phase, let us assume that our voltage and currents both are sinusoid. One case, but here definitely our power flow may not be particularly, it is a constant as like this. Three phase system, the power flow is constant. Is it right? Three phase power. If you just go for three phase power, how the power three phase varies with respect to time. Total three phase power, balanced sinusoidal currents are there. How is the power with respect to time? Our x axis is the time. We are having a 3 kilowatt load, let us assume that three phase. Then how is the power with respect to the time? The power will be a constant in case of a three phase system. Power will be a constant in case of a three phase system. But in case of a AC system, assuming the currents are sinusoidal, then we have seen it here, power will be a uh, it is having two components. Is it right? One will be DC plus other is two times of this. So this will be DC, and then we have seen that power is a fluctuating like this. Okay, it is having these fluctuations of the power. Okay, this is the fluctuation. So this is the AC power. Okay, so this will be AC power. under the assumption that our currents are sinusoidal. Our currents are sinusoidal. So here, so to balance this, here one side we are having a constant power. Okay. Other side we are having a this AC, a conventional. I am talking about the conventional inverter. Let us have a single phase conventional inverter. We are having a DC supply is here. With this, our AC power is varying. Okay, it is not a constant. It is not the constant. AC power is not a constant. And to balance that, one side we are having constant power, other side we require the capacitance is much. That will be a conventional or a single phase bridge inverter. Here also same situation, but here we are not expecting that our currents are sinusoidal. Okay, one important thing is our currents may be the square wave currents. Okay, we are not bothered. We are injecting the current into the system. That is what we are here is we are injecting the current in the system. We are injecting the current into the system, and so here purpose of the capacitor is required. AC side, our currents normally we are calling as the here current, a constant current, square wave type current we are injecting into the grid with this system, let us assume. And our power requirement may be a varying with respect to time. Our power requirement is varying with respect to time, and in that case, to balance the power, we require a filter capacitor. And these are four devices we are having, and we require only the filter inductance at the AC side. We don't require capacitor. Okay, because our this is particularly we are interested in the current. We are injecting maximum possible current into the grid, and so that we require a inductance here as a filter, and then we represented the grid a single phase grid. Neutral is connected, and we are very important is we are having a leakage or capacitance between panel to ground. Whatever capacitance is between the panel to ground and the voltage across it, that particular capacitance between panel to ground, and that voltage across that capacitance we represented as a VPE. Panel with respect to, you can call as earth, or VPE we have given the name here, whereas VPV is the solar panel output voltage. And this is our conventional inverter we are having, H bridge inverter you can call it, or single phase full bridge inverter. And now we have seen it here already. We discussed this, that how we control this a single phase bridge inverter. And for controlling the single phase bridge inverter, we are having three methods or three techniques, you can call it three. We are having the PWM techniques three. One is a bipolar, then unipolar, and then hybrid. Okay, we'll discuss one by one these techniques. And what is meant by a bipolar? So already bipolar means here our, if you go for this diagram first, this will be our, here our inverters we are having, names are given. I will just try to sketch the figure of here inverter. Let us assume that I am trying the inverter here with just representing the switch. Okay, so this will be our DC side, and from this we are having the AC side here. Okay, this is the AC side and DC side, and numbers are here. This is given names as one leg we are given here, names are different we are given. One leg is S1 and S2. Okay, and another leg is S3 and S4. Okay, that convention we have taken from one book. Okay, I'll give the reference of that book. We are adopting the same convention. So here we have seen that this will be a numbers given. If you go back, this will be S1 and S2 will forming the one leg, and S3 and S4. So here S1 and S2 forming one leg, S3 and S4 is forming the other leg. So that will be a configuration. And bipolar, we have seen that these opposing switches, these opposite switches we on and off simultaneously. When S1 and S4 are on, S2 and S3 will be off. When S2 and S3 will be on, S1 and S4 will be off. And here when S1 and S4 are on, let us assume that here we are having a modulation PWM technique, a high frequency carrier wave, and a high frequency, particularly carrier wave or triangular wave, and we are having a modulating wave of 50 hertz, you can call it. When S1 and S2 are on, we say that our output voltage is positive. Whenever here, if you this here modulating wave is higher, S1, S2 will be more on, and when S1, S4 are on, sorry, when S1 and S4 are on, our output voltage will be positive. And when S3, S2 are on, our output voltage will be a negative. So here output voltage is varying from plus VDC to minus VDC. Okay, no in between, zero. So output voltage will be our varying from plus VDC to minus VDC. Two switches are on simultaneously, cross switches are on, and based on that, so how will be our path of current flow? Let us assume that our positive output current. What is mean by the positive output current? Our current is flowing with this direction from upper side. This direction of current we can call as the a positive current. This we can call as the positive current, and here we assume the two switches are on. Okay, positive current will be provided by two switches, and these two switches are S1 and S4. So here we say that the S1 and S4, these two switches are on, they are on. These two switches S1 and S4, these will be on. And how is the path? So S1 is on. Let us start from this, a positive from this. Already it is marked S1 to the S1 switch. From A point it goes to the load, to the grid. From the negative through the S4, it completes the path. This will be a path here, what we are having. So this will be a when current is a positive. When current is a positive. Current is positive, but it is operating at a high frequency. It is operating at the high frequency. Current, yes, any question? So we are having our current is at 50 hertz. Okay, so whatever our current, that is a positive half cycle we are considering. So this is a positive half cycle of current. This will be our current for a positive half cycle. And in positive half cycle, so many times S1, S4 will on for some time, and after that S3 and S2 will be on. Okay, in the same, because it is a 20 millisecond we are having a 10 millisecond half cycle period. In that case, it is a few microseconds. S1 and S4 will be on. After that, S2 and S3 are on, but current will remain the same, though it is a S3 and S2 are on. So let us go for S2 and S3 are on. Okay, S2 and S3 are on. Though S2 and S3 are on, but here current is positive, and we find a path here, not from this. So okay, let us go for next slide. 1 minute. So made some mistake. Positive output current, negative output current. Okay. So okay, we're not shown the, whenever these two are off, I will just try it here. Now let us suppose that our these S1 and S4 are off, but now current is positive, though S3 and S2 are on. S2 and S3 are on, current is positive direction. Then in that case, how is the current will flow? This current will be there. Okay, the positive current will be there because it is a positive current. This current will be here. Okay, from this B point, it through a D3, it will go through this, through a capacitance, you can call it. Okay, and then through this, it will complete the path. So here we see that this is a freewheeling operation, you can call it. Okay, or you can call it when the current is a particularly, voltage will be remain same because A point is connected to the particularly here a particularly voltage polarity will reverse, but current will be showing in this direction. Current will be in the same direction, and this will be, we have seen it here. There will be exchange of energies taking place between L1 and CPV. So there will be exchange of energy between the capacitance and inductance. Whenever we are having a freewheeling type operation, in that case, there will be a definitely exchange of energy between the inductor and capacitance. And this is a, we can call it as a reactive power flow. This is actually a exchange of power, exchange of power between inductance and capacitance. Now the current will flow through between these two, and this will be a lead to a low power factor, and this is not the advisable. Efficiency of the inverter will decrease. So one drawback we can say here, one drawback we can say here is say here is there will be exchange of power between the grid inductance at the grid side and capacitance at the solar panel side, and our interest is that should not taken place, that should not taken place, so that the reactive power flow between L1 and CPV should not be there, that we want to avoid. Now here, what is the voltage across the inductor? So here we have seen that either the voltage appearing across the inductor is plus or the minus. Here voltage across the inductor is varying from plus VDC to minus VDC, to minus VDC to plus VDC. So this is another aspect we are having. So voltage across inductor is varying from plus VDC to minus VDC, or plus VPV to minus VPV. That is the another. So this is the operation whenever we are having a positive output current. This is a particularly for the positive half cycle. Okay, positive half cycle. Our current, when the switch is on, current will flow. S1 and S4 are on, current will flow through this. And our current is positive, so whenever S1 and S4 are off, but current is positive, in that case the freewheeling path will be through a D3 and particularly D2, and which during this period we have seen that there is exchange of power between the inductance and the capacitance, and that we should not require. So this will be continue for particularly half cycle 10 millisecond. This will be on off will take place, and we are having a power exchange, and voltage across the inductor will be plus VPV to the minus VPV. When diodes are conducting, B is connected to plus VPV. When switch is on, our B is connected to the minus VPV. So plus VPV to minus VPV, that is happening. Now in case of negative half cycle, our current, again we can show the two operation current whenever opposite that S3 and opposite this S3 and S2 are on, and our current will flow from S3. It will be opposite direction, negative current through a load, then through S2 it will go back. So this will be our conventional negative current. But whenever this S3 and S2 are off, and the current, they will find a path, freewheeling path. We are not shown it here, but freewheeling path I will just show it. It will be from this side, the same negative current. It will find a path through a diode, okay, and through the filter capacitance, okay, and through this D4, which the switches are off, through which it will complete the path. So this is the path of current. Okay, negative half cycle, we are talking about negative half cycle. The switches are operating at high frequency, and again here exchange of power is taken place. So this we have shown it normal operation and freewheeling operation during negative output current and the positive output current. And already this technique, how to generate the PWM switching signals, how to generate the PWM switching signals, that we are already discussed. We are having a modulating wave compared with a high frequency carrier wave. Simultaneously cross connected switches we can operate. Okay, becomes so S1 and S4 will on, we are having. So whenever our modulating wave is higher, our S1 and S4 are off. Whenever modulating wave is lower as compared to carrier wave, S3 and S2 will on, give a negative voltage. Here our S1 and S4 will on, but if you see it here, our voltage is modulating voltage is less as compared to carrier wave, and here in this period our switches S3 and S2 will operate at the negative side. So this will be a voltage at the output, either it is plus VD or plus VDC or plus VPV and the minus VPV. We don't have a zero voltage. And because of that, what will happen? So here we'll just whatever discussed, we'll just make it here features what we have discussed. Leg A, B switched synchronously in the diagonal. That is means S1 and S4 are on simultaneously. S2 and S3 are on. And we just discussed our output voltage waveform. We don't have a zero voltage state. Anywhere our voltage will not be a zero voltage. And now the voltage across the that leakage or voltage across this capacitance between the panel and ground, and that waveform if you simulate it will be a power frequency. We are in 50 hertz power frequency. Okay, 50 hertz power frequency. No switching frequency components appear, particularly in case of this capacitance between the panel and the ground, or you can call it. And here because of that we can say that low leakage current and EMI. That is the benefit. So okay, this is one required feature is available, but what is drawbacks of this scheme? So here our switching ripple correspond to switching frequency. So here ripple current is more and we require more filter inductance. And we have seen that voltage is changing plus VPV to minus VPV, minus VPV to plus VPV. And because of that, this is voltage appearing across the inductor. And because of that, our core losses in the inductor will be a more. And here another reason is we have discussed a freewheeling operation. And we have seen that during freewheeling operation, you have shown the currents here. This blue current you can take it, and this blue current you can take it. Where we have shown it here, there will be exchange of reactive power between the L1 and CPV. And because of that, definitely losses will increase and definitely the lower efficiency. So this technique, though we are calling as a bipolar modulation, okay, we are having a low particularly the leakage current, that will be added advantage. But here we have seen that voltage across the filter inductance and the reactive power exchange, these are not the good features. And that's why this particular full bridge inverter with bipolar is not suitable for a PV application. So any question? So we are discussing why bipolar switching, bipolar modulation for a single phase bridge inverter, and that is not suitable for PV application. Reason is losses in the inductor and the reactive power exchange between the inductance and the capacitance during the freewheeling period. Any question? Any doubt? Hello, am I audible?
Yes, sir.
Now let us go for unipolar modulation. We are already discussed, I think, unipolar modulation. Is it we are discussed in our very first few lectures? Can you recall? Okay, we are going for here. Again, we are having the same inverter. Okay, so we'll just draw the inverter here. So we are having a bridge inverter, single phase bridge inverter. 4 switches, we'll just draw it here. So in one leg, we are having switch numbers are S1 and S2. That is the, okay, we are conventional is here different. We are having a first leg devices are S1 and S2. Our convention, earlier convention was different. This book we are used, convention is different. Okay, you can stick to this. And then second leg, we are having the device is S3 and S4. Okay, so this is our what we are having the 2 switches. This is the input side is DC. Okay, I'm not showing all details. And this is our output AC side. This we are having. So this is our inverter. I'm not showing, and diode and all this. Just for simplicity, here anti-parallel diode will be across each switch. But now here we have seen that. So here one leg we are controlling independently. So earlier case we require only one signal, but here we require two signals. One signal for controlling the one leg. Here S1 and S2 we can't on simultaneously because DC will short circuit VSI. So when S1 is on, S2 will be off. Okay, so one switching signal we generate for first leg, another switching signal we generate for a second leg. And this for first leg we are having a sinusoidal modulating wave, whereas second leg we are having a modulating wave will be inverted. For second leg our modulating wave will be inverted. So we have to generate the two comparisons we have to make. A first comparison is for first leg S1 and S2. So we are having a modulating wave and a carrier wave. Compare it, we get the signal for S1 and S2. Then we invert the modulating wave. This is modulating wave for second comparison. We invert it and again compare with the same carrier wave, and we'll get the switching signal for S3 and S4. So that is the difference. In bipolar modulation, we require one modulating wave. Here, in case of this, we require two modulating wave. They are out of phase, sinusoids and out of phase. So first modulating wave will control the switching signal, control the switching signal of the first leg and the second leg. And last time we discussed, we make a point N here. This point we can call as N. Here this point we can call as A. And this point we can call as a B. So independently we can take the voltage VAN. So VN and S1 is on, VN will be positive. When S2 is on, VN will be 0. So here VN will vary between positive when S1 is on, VAN positive when S1 is on, 0 when S2 is on. And when S1 is on, whenever modulating wave is higher than carrier wave, S1 will be on. So VAN will be positive. And when S2 is on, or modulating wave is less than carrier wave, then S2 is on, output voltage. So VAN, we see it will be a voltage either varying from VDC to 0 to VDC. Similar, we apply when S3 is on, our VBN is positive. Okay, second waveform. Here we can have a positive. Here modulating wave is less, so S4 is on. So here it will be a 0. And similarly, we can go. So VBN is also a varying from plus VD to 0. And now output VAB. So we are in VAN and VBN, and VAB will be VAN minus VBN, and that will be our output voltage we are having. And this output voltage we have shown it here. It is having a plus VD, 0 and minus VD. So in case of unipolar modulation, we are available 3 voltage levels. Bipolar, we are having only 2 voltage levels. In case of unipolar, we are having 3 voltage levels. And what are these 3 voltage levels? Plus VD, 0 and the minus VD. Plus VD, 0 and the minus VD. That will be what we are having a difference between this. And here, so if you go back now you are having here, so output current is positive. So here, whenever positive current is there, what are the possible options? Positive current, we are having this S1 will be on, and whenever S1, and let us show various 3 possible combinations for positive output current. Whenever positive is, we are having both the S1 and S4 are on. Okay, S1 and S4 are on, and whenever S1 and S4 are on, this will be our path of current. S1 is on, so this is already marked current direction from A to the load to grid, then through S4, then it goes back. This will be a path of current when S1 and S4 are on. So here we say it is a S1 and S4 is on. S1 and S4, these 2 switches are on. Positive current, what will be other options? Because they are operating now, S3 may be on. So S1 is on and S3 may be on. That may be a situation. So S1 and S3 may be on. Both of these are S1 and S3 are on. S1 is on, then S3 is on. Another phase we are having S1 and S3 may be on. Only two switches will be on at a time. Is it right? Only two switches will be on. One is S1 with S4. Other is S1 with S3. Okay. So S1 with S3. We have shown it here. So now the current is positive, so current through this positive current, and it will S3 is on, so through a diode or this, and then through the S1 is on, so this will be our current. So this is you can call as a prevailing. Prevailing current is not going to the capacitor. That is what in case of bipolar, that path was through the capacitor. So here no exchange of energy between the inductor and capacitor. That is what we achieved here. We don't have a energy exchange between the inductor and the capacitor in this case. That is our major achievement we are having. Another is when S1 is on, it is possible that, so next configuration for positive current. So here positive current is there, but this may be S2 is on because both are operating at high frequency. So next is we are having S2 is on, and we are having a S4 is on. S2, S4 are on. S2 and S4 are on. So these are the combinations, possible combinations, particularly for positive half cycle. So positive half cycle, we are having S1 and S4. Then next is S1 and S3. Then we are having S2 and S4. When S2 and S4 are on, when S2 and S4 again are positive current, so S4 is on, so it will be passing this current through this and this. So it will making a path what we have shown it here. So whenever S2 and S4 are on, okay, S2 and S4 are on, then we are having a freewheeling operation. So this is a two freewheeling operations possible. We have shown it here, and how the positive current will flow. So positive current will flow whenever we are having energy is taken from when S1 and S4 are on. Positive current will be taken from supply or from PV when S1 and S4 are on. And other options are here we have shown it here. S1 and S3 may be on, and particularly S2 and S4 may be on. So here whenever S1 and S3 are on, because they are operating at high frequency, whereas our output current is having just the 20 millisecond period of positive remaining, so that here so many switchings will be taken place. So here we have seen that S1 and S3 will be on, so it will be freewheeling is taken place. Another is here we are having a S2 and S4 are on, and because of that also freewheeling will take place for a positive. Similar situation we can discuss whenever our output current is the negative output current. So when we are having the negative output current, and the current will be now here S3, now S3 and S2 are on. So when power will be flowing from PV panel through the switch S3, it will go to the point B. From this it will through the grid it given back from this point A through the switch S2, and this will be our a path of a particularly current, a negative current, right to the left side. That assume we are having a negative current. This is the one whenever power is flowing. Other two cases we are having is particularly upper two may be on and lower two may be on. So whenever we are having upper two are on, a negative current between the S1 and the S3. S1 and S3, and it will making a prevailing path particularly for this. This is the one prevailing path. Another is from prevailing from negative current. It will from S2 and S4 like this. So these are the two prevailing conditions and one power flow you can call it. So first condition, a first condition where power is flowing from PV panel to the grid, where we are having a cross switches are on. And other two cases when upper two or lower two are on, where we are having a freewheeling operation. This is upper two are on, lower to or on a freewheeling operation. And with the help of that, we have seen it here, particularly there is no exchange of power. One achievement is here that there is no exchange of power between the CPV capacitance at the PV side and the inductance at the grid side. There is no exchange of the reactive power flow. That is one we achieve. Whereas the voltage across inductor, we have seen that in case of this unipolar switching, we are having a zero voltage level. That's right. We are having a zero voltage level. So voltage across inductor may be going from plus VPV 0 minus VPV. So here, because of that, definitely core losses in the inductor may become a smaller one. So this is we have discussed. Now, so what will be features of this? What we are having discussed? Leg A and leg B switched at high frequency. Then zero voltage state is available. Okay, we have discussed these two. Here ripple currents, okay, so is our high frequency ripple, and because of our inductance requirement is low filter requirement, that is one advantage. And we have seen that our three levels of voltage are present, so the voltage across the filter inductance will be 0 plus PV, from plus PV to 0 to minus PV and 0. So definitely because of this our core losses will be less, and it will have a high efficiency, okay, 98%. Okay, this we can say it here. But now, what is the drawback of this? Now here, we are not going for simulation of this. We have taken this graph from the particular simulation VPE. That is the voltage present across the capacitance. That is the capacitance between the panel and ground, and it has a high frequency components. And because of that we are in the high leakage current, that maybe current is high, and that is the problem. So here major problem is we get the improvement in efficiency, but there will be a problem of leakage current and the EMI. So this is again not suitable. So one bipolar, we have shown bipolar, we don't have a problem of leakage current and EMI, but efficiency is problem. Now unipolar, we are having a efficiency is better, but leakage current and EMI is the problem. Okay, so this inverter is now, this technique is not suitable for the particularly PV inverters. Then now let us go for next. We are going for is the hybrid modulation. So third option is we are having a hybrid modulation. So here we are having a two legs. One leg we can operate at a power frequency and other leg at high frequency. So why we are doing this? Sole purpose is we want to reduce the losses. One method is we cannot operate at the high frequency. One will operate at low frequency and other will operate, one leg will operate at, so two switches will be operating at 50 hertz and two switches will be switching at a 10 kilohertz. That may we can say it here. So one leg is switched at power frequency and other leg is at which leg, particularly A leg, let us call this will be our A leg. I am just showing this leg. We are operating the switches S1 and S2. S1 and S2, we are operating at a power frequency. Let us assume that I will call it as a power frequency P, I will write it power frequency. So S1 and S2, this S1 and S2 will operate at the power frequency, whereas S3 and S4 will operate at a switching frequency. So, and here, let us, this switch may be on. S1 is on for how much duration? 10 milliseconds. S1 is on for 10 milliseconds. S2 is off for 10 milliseconds. S2 is on for 10 milliseconds. S1 is off for 10 milliseconds. So S1 and S2, they are operating at a 50 hertz. They will remain on continuous for half cycle of AC output. Whereas S3 and S4, they will be on and off at a high frequency at 10 kilohertz. Now let us consider here S1 is on and S4 is on. Okay, so S1 and S4 is on. Our power flow, we have shown it here. So S1 is on, so power is taken from panel through the switch S1 to the point A, to the load, okay, through the grid, it from S4, it go back. So here our power is flowing from panel to, this is a power flow we'll represent here. Power is flowing from, okay, power is flowing from PV panel to the grid when S1 and S4 are on. But when S1 is on, this S1 will remain on for 10 milliseconds. S1 will remain on for a 10 millisecond. In between, this will now change. S4 will become off and S3 will become on. When S1, now then it is possible that S1 is on, S1 and S3, this combination will on. So let us go for S1 and S3 is on. Our current is the positive, we are considering positive, and positive current is there. And now our S3 is on and S4 is off. So our path of current will be now through the D3, this and this. So here we can say that the power is freewheeling. It is power is not taken from PV panel, but it is a freewheeling. Again, here possibility is that this is a positive half cycle. These two cases we are having. So this will be one case whenever S1 and S4 are on. Definitely our power is flowing from PV panel to the grid. When S3 is on, because S1 will remain for positive half cycle continuously can, either this will be changed. When S1 is on, power is flowing. When S3 is on, freewheeling will take place. This will continue for continue for the 10 milliseconds. Next 10 milliseconds is our negative output current. Particularly next 10 milliseconds, our now next 10 milliseconds S2 is on, and let us assume that our S3 is on. So when S2 and S3 are on, when S2 and S3 are on, so now we have shown it here. So here, go back. So this will be our negative output current. So S3 is on, so our current will through S3. It will go to the point B. Okay, from this grid, it is feeding power. It comes to the point A, and S2 is closed, and this will be we are having this. So this power is flowing from again a panel to the grid. But S2 will be remain on for 20 milliseconds. Then change, maybe S3 will become off and S4 will on. Next is we are having a S2 and S4, these two are on. When S2 and S4, when when this S2 and S4 are on, our current is negative. So negative current again prevail through this on switch S2, and then S4 is on, it will be on through this. Okay, so this will be our, what we are having is here no exchange of reactive power between the panel and the uh, between, sorry, no exchange reactive power from capacitance to the inductance. That benefit we can have. So here what are the advantages we can have? Again, the low reactive power exchange or no reactive power exchange, so the efficiency is better. Again, our voltage is varying from 0 plus PV, 0 minus PV, so that efficiency is better, core losses will be less, efficiency will be better to around 98%. So it is having, again, the efficiency is better. But now again the drawback, here we have seen that whatever the voltage appearing across the capacitance between panel to the ground, that is a square wave type waveform, will be present at the capacitance, and because of that we are having a high leakage current and EMI. So though this earlier, next to whatever bipolar, we don't have a leakage current and EMI problem, but these less efficiency. Whereas unipolar modulation and hybrid modulation, we are having a better efficiency, but we are having a high leakage current and EMI. So we conclude here that conventional bridge is not suitable. This bridge is not suitable for a PV inverter, as a PV inverter feeding power to the grid. And now we need the improvement in this. We want to have a new topology for this single phase PV inverter, and what are the new topologies that we can discuss next lecture. So we'll meet tomorrow at 10:15 a.m. So any questions? Whatever we discuss, we are just already we have discussed these three things. Okay, single phase bridge inverter having a bipolar switching, unipolar modulation, bipolar modulation, and hybrid modulation. And our perspective is from particularly application, solar application, feeding power to the solar, feeding power to the grid. If you are having any doubts, hello, am I audible?
No. Yes, sir.
Okay, so we'll meet tomorrow at 10:15. Okay.